Hi guys, good morning or good afternoon or good night. um, but I'm going to be here to record a lecture about soil water, which is the content in chapter 5, the next chapter we're going to be going over. And in particular, this lecture is going to cover the material in the first 3 sections of chapter 5, which is first of all about water structure and properties, second of all about capillarity, and third of all about soil water energy. And then I'll record another lecture about the next kind of half of the chapter. So I'm going to share my screen with you. Here we go. Okay. All right, so first of all, we want to think about how water works, what water is, in order to understand how it's going to move in the soil. And a lot of people already know that water is H2O, or 2 hydrogen and 1 oxygen atoms bonded together. And you may also know, or may not know, that the water molecules are structured in such a way that we call them polar molecules, or in this case, dipolar molecules. And what that means is that the electrons that surround the outside of the atoms are organized in a certain way on the molecule so that they are concentrated on the side of the molecule that has the oxygen, and then they're kind of absent, or they're less likely to be hanging out in the part of the molecule that has the hydrogen atoms. And what this means is that the water molecules have a slightly negative charge, shown by this lowercase delta negative in the image. The delta is that like cherry looking thing on the diagram there. And then the other side of the atom the molecule has a slightly positive charge. And so most molecules don't have a charge, and they don't really bond to each other that strongly. But these polar molecules are able, because of this slight charge distribution, able to create what are called hydrogen bonds, or these fairly strong bonds in between the different molecules. And so this causes water molecules to have a cohesive property, where one water molecule coheres or bonds to another water molecule in a very strong manner, again, stronger than most other molecules in the environment would experience. They also have an adhesive property, where a water molecule will stick to a different surface, so like a plant root or a clay particle or a sand grain, in a pretty strong way, again, because of its charge. And then also it has strong surface tension. And what that means is that along the water surface, have this water like pooled up on the surface of the soil, or pooled up in the water table below the soil, the water molecules along the surface have extra energy to use to bond onto each other. So they're bonded together in an even stronger way than water molecules that are down below the water surface, where they are using their energy to bond to water molecules in all different directions. So that refers to the water surface tension. Okay, so that's important because it controls the way that water behaves as it moves around in the soil. And one of the important things to understand about soil water is that so far we've really focused on the movement of water down into the soil. We said that was important because we don't want water pooling up on the surface where it might run off the surface and not be available in the soil for later, or it also might contribute to erosion. So we've kind of focused on the value of moving water down into the soil. But in fact, there's also a lot of water movement in the soil that happens not only down, but also back up towards the soil surface in times of the year where there hasn't been recent rain or recent irrigation. And so that water that's stored lower down might be actually coming back up towards organisms that are living closer to the soil surface. And this happens in what are called capillaries. So capillaries are just tiny tubes, right? We have capillaries in our body that move our blood, and these capillaries are really good at moving our blood, which is mostly water, because the water bonds on to the sides of the tubes. And the smaller the tubes are, the better they are at moving water along the tube, because there's more surface area relative to the amount of water that can kind of create this adhesion, this bonding of the water molecules to the surface, and then there's also more surface tension along the water surface. If we want to move water basically upwards through the soil, we need to create tiny tubes in the soil that water can kind of creep along. And this is not going to happen through macropores, but it's going to happen in mesopores, medium-sized pores, or in small micropores in some cases as well. So you can see in the diagram on the top, there's an area of saturated soil water below, the water table, which is the place that's at the top of the soil saturation zone, and then you can see that there's water that's kind of above the water table in mesopores and micropores, but not in those macropores. And then you can also see these tubes of varying widths that are stuck into this dyed blue water, and you can see how the water in the smallest tube moves a lot higher than the water in the bigger tubes. And so in the soil, we want macropores. We've talked about their value already, but we also probably want to have some variety of shapes and sizes in our soil to allow for some capillary rise or some vertical movement of water in the soil as well. Of course, the tubes in the soil are not perfect glass tubes, like we can see in the picture in this slide. They're not quite straight. They have little air bubbles that are in them, so they're not quite as efficient at moving water, but nonetheless, they can allow water to move in this vertical way. Okay, so the next concept that we want to talk about is soil energy, because energy is what does the work of moving the soil. Energy being the capacity to do work, work being the application of force over a distance, force being a push or pull of an object, like a water molecule, from an interaction with another object, like another water molecule or soil surface or the Earth's core, something like that. So there's lots of forces that are exerting energy onto the water and causing that water to move around. And that energy can be in the form of potential energy, or PE, which is a form of energy that is essentially stored in something that contains that energy, like in a water molecule. And this is often energy that's based on something's position. So like if you're a raindrop that has used the sun's energy to evaporate that raindrop off the ground and pulled it up into the air, now that it's up high in the air, it has the potential based on its position to fall back down to the ground and do work in the process. So that would be its potential energy. There's also kinetic energy, which is the energy that is based on current motion. So if you are a raindrop falling down from the sky, you can do some work along the way. You can push other water molecules as you go, or you can slam into the ground and break up a soil aggregate as you hit the ground if it's not covered. So that would be kinetic energy versus potential energy. Okay, so we know in the environment and in the universe, things are always moving from areas of higher energy to areas of lower energy where they're more at rest. And so basically, when we think about this or talk about this in terms of water energy, we talk about water moving from a high potential or high potential energy position to a low potential energy position. And this movement is always going to be from a higher potential, a higher energy, to a lower potential or a lower energy. And there are 4 different kinds of forces that can be acting on the soil water that are being these pushes or pulls on the water molecules and determining how they move around. And the first one is called the matrix potential, then the osmotic potential, the gravitational potential, and the hydrostatic potential. So the matrix potential is the attraction of the water molecules to the soil matrix or to the soil solids like the clay, the sand. And since those particles exist all around the water, this can pull the water up, down, left, or right. Osmotic potential is called that because of osmosis, the movement of water through a semi-permeable membrane, something like the soil that small things can move through, but not big things. And so basically in this case, water moves around through the soil medium and it moves towards solutes, things that are dissolved in the soil water. So where more solutes exist, then the water is going to kind of be concentrated in those areas. So those solutes are things like salts, like ions, cations like calcium or potassium, sugars, other things as well. And so the water can move, in this case, in every direction, just always going towards where those solutes are located. Gravitational potential is because of the Earth's gravitational force, right? We know that the Earth pulls things down towards it. Water is not an exception. And so water is going to always be constantly experience this downward pull. And then finally, the hydrostatic potential is the potential that is created for water to move based on pushing of water by other water molecules. So if there's a bunch of water crowded together in a saturated soil, some of that water can kind of kinetically push on other water and cause it to move. Like if we have surface runoff, the water molecules are pushing on other water molecules and causing them to move. So we set up what's called the water potential equation. And basically these trident looking symbols are capital psi, capital Greek letter psi. And so psi stands for water potential. The water potential T, psi T, is the total water potential that is contributed or determined by looking at the psi G, gravitational water potential, the psi M, matrix water potential, the psi H, hydrostatic water potential, and psi O, osmotic potential. And as we already said, when we add all these things up and get the total water potential, then we can look how the water is going to move in the soil, because it's always going to be moving down gradient from the higher energy or higher potential area to the lower potential area. So that maybe down, the water might be infiltrating or draining into the soil, but in certain situations, the water might actually be moving to the left or to the right or back up towards salts or towards plant roots or organisms in other situations. So we'll go through each of these kind of potential components in a little bit more detail, starting with the matrix potential. So the matrix potential is basically the bonding of the water molecules onto the soil surface. And this happens because the soil surface has a slight charge. We've already learned that clay particles in particular usually have a negative charge. The polar water molecules can actually bond onto this negative charge. And so the more soil surface area there is, the better that water is going to be able to bond onto the soil. Also, when there's a lot of dry soil that's not already kind of fully occupied by water molecules, then there's going to be a stronger pull for those water molecules being attracted towards those negative clay surfaces. Whereas when the water is already attracted, or there's already water molecules coating soil surfaces, then there's not as much additional pull. So the range of the water potential values that we would have for a matrix potential are 0 in a saturated soil. In this case, all the soil matrix, or all the soil particles, the clays, the silts, the sands, are already completely bonded to water on all their available surfaces. And so there's no pull of water towards the surfaces because they're already maxed out with water. And then if a soil is dry, or there's available soil surface that can be pulling on a water molecule, then it would have a negative water potential. Because remember, the water always moves from higher potential to lower potential. So if it's going to move from a wet area to a dry area, and the wet area or the saturated area has a 0 water potential, it has to move down gradient to a negative water potential in the dry soil. And you may have seen tensiometers before. You may not have used that term for them, but there are these little tools that you can stick in like your house plant or in some sort of potted plant or garden setting, which tells you like if you need to water your plant or not, how dry the soil is. And essentially this tensiometer is measuring the water potential. And as the matrix potential gets more and more negative, as water is being pulled away from the tensiometer towards the soil surfaces, then the dial on the tensiometer will start to change and point to different things. And they may actually be numbers, or it may be just like a green, a yellow, and a red. And the dial might turn as the matrix potential drops to start to say, water me. And then might, as it gets really negative, say like, help, water me now. And basically it's measuring this water potential in the soil. Another way you can observe this is when you water your plants or you see irrigation. The irrigation is not actually watering every part of the soil, but when there's a saturated zone of soil where the water has been coming out, the water will move away, not just down through the soil, but away from the saturated zone towards the drier soil horizontally, as the dry soil surfaces are exerting a force or are pulling on the water molecules. So you can see in this case that the water is moving out towards these what appear to be green bean plants, away from the area where the drip irrigation dropped some water. Okay, then the next water potential is called the osmotic potential, and the osmotic potential discusses the force that solutes, things that are dissolved in the soil water, have on the water. And basically these ions, salts, sodium, calcium, potassium, have on the soil water is that they bond to the water, and then when the water is bonded to these solutes, it's not as likely to move off-site into another location. One, because it's like bigger, just can't move through the soil medium as well, and it's just more kind of stable. And so when there's lots of solutes in a certain zone, the water is more likely to stay there and not move away to an area where there is fewer solutes. Vice versa, if we have an area where there's really clean fresh water, that water is going to move away from that freshwater area towards an area where there's more salts. So the idea is that where there are salts, it actually slows down the movement of water potential relative to or with respect to an area where there's pure water at STP, which is standard temperature and pressure. So like at room temperature at sea level. And this often happens around plants. So the way that plants actually pull water into the plants is they concentrate solutes inside their root tips, and then the water molecules flow through the cells, which are semi-permeable membranes, by osmosis. Then they bond on to the solutes inside the root, and then they stay in the root, and then the plant can move them with capillary rise up through the plant, through its xylem cells. And that's how plants get water. Now, if we have a bunch of solutes concentrated in the soil outside the plant root, that might actually interrupt this mechanism and cause plants to wilt if they can't get adequate water. And this is one of the problems with having salt buildup on soils, is because it kind of breaks down this mechanism by which plants can pull water into their structures. So in this case, you would have a 0 osmotic potential if there's no solutes, if you're just in a zone of completely pure water. And then the saltier it is, the more ions there are, the more pull those ions would have on the water. And so the water potential would get more negative. They're not going to move away from the solutes. They're going to move from the freshwater zone, the 0 water potential, towards the more negative, lower, saltier zone. Okay, third is the soil gravitational potential. So in this case, we know that gravity pulls things down towards the earth. We've all experienced this anytime we drop something before. And water is no exception. Raindrops fall from the sky down to the ground. Water infiltrates from the surface down into the soil profile. And in this case, we measure the water potential from some sort of reference point, which is usually kind of at the bottom of the soil. So the place where we would kind of have water infiltrating down through the soil, and then it might hit some sort of like rock or barrier that would prevent further infiltration. And we would say once the water is there, it is at 0 water potential. It has no potential to keep moving down. And then we would say if the water is above that point, like up on the soil surface or even a few inches down in the soil, it has a higher potential. And the higher it is above the reference point, the higher the potential is, and it's going to move down, 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 down until it eventually has a 0 potential to keep moving when it's physically being blocked by some sort of like rock or some sort of barrier. So in this picture, the water above the ground has a high gravitational force, and then it's going to move until it hits the ground, and then it's going to move into the ground. Okay, then the final water potential is called the hydrostatic, or sometimes also called the pressure potential. And this only applies to saturated conditions, meaning times when the water is completely filled up, or the soil is completely filled up with water. There's no room for air in the pore spaces. Everything is filled with water. And in this case, there are so many water molecules around that they're actually pushing on each other. They're having sort of a kinetic pushing and pulling, mostly pushing, hence the pressure potential. And so in this case, you have a 0 water potential if you're above the water table, if you're in the unsaturated zone. In that case, there's just not enough water molecules around to actually be hydrostatically pressing on one another. But if you're below the water table, you could have a positive pressure potential. You could be experiencing a push, and how big that push is depends on a lot of what's going on in the environment around the saturated zone. But if you have a bunch of water that's like flowing downhill into a saturated zone, there could be a lot of force of water pushing down on other water molecules. And then if there's some sort of crack in the rock, water could be rushing out of that crack in a spring or an artesian well. Or maybe we create an artificial crack, we drill a well down into the ground, and water can come up to the surface there because the pressure at the surface is actually lower, right? Above the water table has a 0 low water potential relative to the pressure below. And the water is moving from the place where it's experiencing a lot of push to a place where it is not experiencing a lot of push up at the surface. So this would be another example where sometimes water actually moves upwards, which is, of course, not the direction that we normally think of water moving. Okay, I think that wraps up our discussion about water energy. So I'm going to stop this lecture, and then I'll record another one about the second half of chapter 5. All right.